Bismillahirrahmanirrahim. Today's video is about Exponential Fourier series, chapter number 17, from Mr. Alexander and Sadiku's book of Fundamentals of Circuit Analysis. And here we'll be solving example 17.10. Actually, we'll be discussing this. Now, I hope you have learned or you are familiar with the Fourier theorem. This is a very, very interesting theorem. And the main theme is that it says that any practical periodic function of frequency this can be expressed as infinite sum of sine or cosine functions. That means any function, any signal can be constructed by adding sine and cosine terms of different frequencies. Like here, you have cosine terms of first harmonics we call, then sine first harmonics, then cosine of second harmonics, sine of second harmonics. This way, you can add as many as you want to get the perfect signal. Now, this can be simplified. We just collect the cosine terms and the sine terms, and this is DC term, so DC plus AC. But we need to further simplify as we go on to express it in exponential form. For that, we'll be using the Euler's identity. I hope you remember this. Cosine is given by the exponential form, similarly sine. So we'll be using these two in this 17.3 equations. So plugging in for cosine and plugging in for sine, the exponential terms, and then collecting the like terms. That means Ej n omega t, Ej n omega t terms will collect. Now, point to note is that here it is an, so we write an, but here it is plus bn. Now remember that 1 over j can be written as minus j. So we are writing that, so it is minus j and then bn, and the e raised to the power j n omega naught, and similarly for the other case also. Now in this case it will become plus, because when j goes up it will be minus plus. Okay, so this equation now we'll try to simplify further, and that is if we write this equation, this an minus jb divided by 2, and we call it cn, and similarly the other one we call it cn minus, and the first one, the DC component, we also call it c, but C0. All terms are in terms of a C. So this equation will now become as here, and it can be further simplified if we collect all the C's. So all the C's here, and now the limit is from minus infinity to plus infinity. Remember this one, we were from n to 1, and then in the case of a negative it will be n to plus infinity it was here, and then it will be minus infinity, and that will also include 0 term, that is C0. So all the terms are included here. Let me explain it one more time. You can see here n is positive and here n is negative. So that is why we are now going from negative infinity to positive infinity, which should also include n is equal to 0 for this one. So this is the simplified form of the function. Now this is the complex or exponential Fourier series representation of the function ft. Now, how can we find the value of Cn? Well, we can find the value of Cn from here, but there is an easy way also, that just like the inverse Laplace transform or inverse Fourier transform, we can find Cn by the integration method. 1 over t integration ft e raised to the power minus jn omega t dt, where omega n is 2 pi over t. So Cn, we have this equation. Now we to plot the plot of magnitude and phase of Cn versus n omega are called, first one is called the complex amplitude spectrum, where we are just plotting the magnitude, and then the complex phase spectrum, where we are plotting the phase angle. Okay, with this background, now let's go to the question. Find the exponential Fourier series expansion of the periodic function ft equals e raised to the power t, and this is we are talking about the time period from 0 to 2 pi. But this equation is actually to show that this function is periodic function, because ft plus 2 pi is ft, so it is repeating. I hope you know how to write the periodic functions in this form. Okay, now from here you can see that t is 2 pi, and we know omega naught is 2 pi f or 2 pi over t, and t is 2 pi, so it will be 2 pi over 2 pi is equal to 1. And when we say find the Fourier series expansion, that really means that we got to have something like this. We'll try to achieve this type. And in our case, it will be like this, because the DC component is also inside this. So this is what we are trying to find. And as we had discussed, the coefficient Cn can be written in this form. So let's find Cn first of all. We'll put in the value of ft from here. So ft is et, and omega naught is 1, therefore ej n omega naught t will become e minus j n t. And now we can just add the powers. We need to integrate. For that, I hope you remember this type, that if integration of e raised to the power ax dx is 1 over a ex e power ax, and then you can write some constant. We don't need to write it here. Okay, so this is what we have done. 1 over a e raised to the power the value, and the limit is from 0 to 2 pi from here, and this was already there, 1 over 2 pi. Now combining these two and then putting in the value of t in this, so we get these two terms. This is being e raised to the power 0 will be 1, so it is 1, and we separating these two now. E raised to the power 2 pi and e raised to the power minus j 2 pi n from here. So we were here, and we got to eliminate this term, and this can be eliminated from, again, the Euler's equation. E raised to the power j can be written as cos 2 pi n minus j sin 2 pi n. Cos 2 pi n will be 1, and this will be 0. So e raised to the power minus j 2 pi n will be equal to 1. So here we will replace this by 1. So replacing, now this is our Cn, and we take this as a numerator. Now this term is a complex term, so we have to separate this. Okay, and now if you solve this portion with the calculator, you should get 85. Now let's see. we go to this fraction part. The numerator part is e power 2 pi. So let's put a bracket, shift e raised to the power 2 into pi, shift pi. So e raised to the power 2 pi, move ahead, minus 1, bracket close. So the numerator we have entered, the denominator is 2 pi. So 2 into pi. So all entries done. Let's move ahead and find the value. So it is 85.066, or we can simply write it as 85. And now we have to take care of the complex part. This one is, you can see 1 plus jn. So this we know that to divide, we have to convert it into polar form and the magnitude and angle relation. So this was the original function. Now we can plug in the value of Cn. So Cn ejnt. We may want to plot the complex frequency spectrum of Ft. So actually, Ft is this function. Actually, you can plug in the value of Cn here, so that will be the answer. But we want to plot also. So to plot, we have to find the magnitude and angle of Cn. The magnitude, we got it from here. Using this relation of the complex form, we'll convert it into magnitude and angle. So this will be 1 plus n square, this is square, and then the angle will be tangent inverse n from this, but because there is a negative sign here, in our case it is positive sign, therefore the angle will be negative. And if we take this up, so we can write it as positive tangent inverse n. So the magnitude is this part and the angle is tan inverse n. Now these two we need to plot. For that you can write a simple program in the MATLAB. I have another video where I have actually done this to show you. I'll give you the link, you can follow. So this is the command which will not be executed. This is just for our reference. Then we have taken the range minus 5 to 5. Then we have defined Cn from here, 85 divided by square root 1 n square. But because there are so many values of n, and Cn has to calculate for all the values, that is why the technique is to put a dot here. So 85 dot division, and here also dot power 2. And then for the discrete time signal, instead of a plot command, we write a stem command. So stem x-axis and y-axis. And so this type of plot you will get if you try yourself. So this was the magnitude plot. Now let's see the phase. Same way, this is just for the reference. This is the limit. Now a very important point, that for theta you don't write tangent inverse minus 1. Rather there is a MATLAB command called A10 or A10. A10 of n, and then same way stem of the variable n and then theta, and the plot will be like this here. So this is how you can get the plot. Now just for your reference, this is the plot given in the book. So it's quite similar to what we have got. And similarly, The plot for angle in the book is this one, which is also matching what we found. I hope you have been able to follow this. Please let me know through your comments. Share this video with your friends and enemies. Thank you.